Jared says, can I ask a quick question about the homework? Of course you can. Of course. Not imbecenti. I don't know if I believe you. Let's see. Let's update this. Where we are given momentum and body frame coordinates, are we to assume the number before the parentheses is the mass component of the momentum? Let me pull up that homework really quick and take a peek so I make sure I know that we're referring to the same thing. Is this... Okay, which problem will this be? Oh, okay, the first one, right? I can't think you can... I don't think you can assume that's the mass. Yeah, you can't. But I don't think you need the mass explicitly to solve this. Yeah, okay, we're talking about the same thing now. Yeah, because I don't think... Because you're talking about this, and you're saying, like, is that mass and the rest velocity? Yeah, so I don't think you can say that. Do you feel like you need that? Hey, you're welcome, Jared. How's the homework going for everybody? I think the quadcopter problem is very cool again because you're calculating the force on the quadcopter from that data. And for part C, okay, so like actually problem 3 is similar to problem 1, because like in problem 1 you determine the total force on this F104. Now for problem 3 you're determining that total force on the quadcopter for the duration of this maneuver that it does. So it's a real life calculation, which I think is great. And then part B, you calculate the weight force in body frame coordinates. But I like part C the best because you take this total force and you get rid of the weight. And when you do that, what you're left with is the thrust and the aerodynamic force. So like this is the force that's keeping the quadcopter in the air. And you're gonna see the force in the body frame Z direction. So like the force that's pointing down, you get a negative number, meaning that the quadcopter is net producing an upward force, which makes sense. I mean, the quadcopter's flying in the sky, so you gotta find that. Okay, Ian says, I have a question on problem 2. Why is u dot equals 5 when the first component of v g relative to O is a constant of 200? Let's see. I'm clicking on the wrong thing. So you're saying y is u dot equal to 5 when this is equal to 200? Oh, yeah, I see, Jared. Shouldn't u dot be 0? Well, remember this, that this is the inertial acceleration or velocity. This is the inertial velocity. Now this is kind of tricky. So you're saying, okay, the inertial velocity is a constant, right? So how is it that u dot is non-zero? Doesn't that violate that the inertial velocity is constant? No, but it's very tricky. Okay, come on, let's go over here. Let's do a quick aside. Maybe I'll do it. Let's just go over to the side real quick, all right? So let's do this. So if you have the inertial velocity of the center of gravity with respect to the origin, if that's some constant, okay, what does that mean? Well, it'll be a vector constant. Well, that, when we say constant, with what frame are we referring to? Well, actually, to be specific here, we should say this. Oh, EX. Oh, we should be careful here, because in our section, I've been using B to denote body frame, right? But in the homework here, it's using E. So I don't want you to get confused here. So when you're seeing E, oh yeah, you're right, Ian. Those are body frame. But this makes me want to go back and change this, you know. Because I think Dr. Lagore's section is now using E's right now. Oh my god, I thought E was fixed frame. No, that should be B frame. F. I'm sorry about that, because you know in our section we've used F for the fixed frame, not what Dilly said, but we've used F for the fixed frame, and we've used B for the body frame. Okay. But this is, you got to remember too that this is at one instant in time. Right? And so what are we looking for in this problem? Let's go over here. Find the components of the acceleration of the center of mass in the body frame coordinates. So this is a transport theorem question. Because if I get the inertial acceleration, so that's what it's asking for. So the acceleration G with respect to what this is the time derivative with respect to the f frame of this inertial velocity and then from the transport theorem, this is going to be the time derivative with respect to the body frame of this plus the angular acceleration of the body frame with respect to the fixed frame and the cross product of that with this. So T37 is in a bank turn. It's measuring the following accelerations and rates. Find the components of the acceleration of the center of mass in body frame coordinates. So if you calculate this out in terms of, you know, these body frame components up here, this will give you that inertial acceleration expressed in the body frame. And that velocity, Ian, is not a constant. Or wait. Sorry. If the velocity vector is constant in the body frame, I guess what I'm saying is, this is always tricky, but if the velocity vector is constant in the body frame, then that means that this term goes to 0, right? So like if these terms are constants, then this goes to 0. But that doesn't mean that overall the inertial acceleration is 0. U dot 5. Are U dot V dot W dot the first term in the transport expression? Yes. Yes, they should be, because we defined I see what you're saying. Hold on. Because this, if we express this in the body frame, we call that U, BX, BY, BZ. So if I take the time derivative with respect to the B frame of this, oops, then this would be u dot, well, like all of these things with just a dot out in front. Okay, so that's true. So then if u dot, let's go back to the assignment. So you're saying that, okay, because I have this velocity and there's a constant here, that how is it that u dot is non-zero? That's what you're saying, right? And the only way I can make sense of that is if this velocity was just measured at this one instant in time. Because actually, we're going to talk about a banked turn today. And in a banked turn, does it make sense for the velocity with respect to the body frame to be constant? Okay, how about let's come back to this, okay? Because I think the stuff we do today will help shed some light on this too. So thanks for bringing this up, Ian. Let's come back to it. I see what you're saying. We will talk about a banked turn today. All right, let's turn down this music a little bit. All right. Oh, no. I think, no, Ian, I bet a lot of people are benefiting from this discussion right now, and it's relevant. So thank you for bringing it up. You guys are always welcome to bring up questions. And we'll work through it. We'll get to the bottom of it. So we'll definitely come back to this. And hopefully what we cover will enlighten this a little bit. Okay, so we're talking about reference flight conditions. So what are these? These are like nominal flight trajectories. Like a banked turn is a reference flight condition. So these are nominal flight trajectories about which we linearize our aircraft model. And let's bring this up again. Like, why are we linearizing things in the first place? Why don't we just go with the nonlinear model? So having a linear model allows us to quickly and efficiently design flight controllers. So if you want to take, I'm teaching digital control systems in the spring, or if you might be taking control systems with Dr. Singh right now. But if you have a linear dynamic system, there's a lot of control theory for linear systems that allows you to just like quickly and efficiently make a controller. And on top of that, we can employ linear analysis techniques like we use in MAE 340. For example, the most basic thing from 340 is assessing the stability of a system. And there's a couple ways that we assess stability, but if you remember, one way is you look at the eigenvalues of the A matrix in the linear state space model. Well, nonlinear systems don't have eigenvalues. I mean, if you think about it, like one of the definitions of a linear system is that you can put it in like A, B, C, D form for state space. If you can't even put it in that form, you can't get eigenvalues, and it's so there's a lot of reasons we like having a linear model, because it's just easier for us to analyze. So okay, if we want to do that, when given a reference flight condition, our first task is to identify the we can call them equilibrium conditions, or we'll call them like equilibrium or nominal values for the aircraft states. Oh, and I should have put and inputs here, because it's not just the states. And we've been denoting these nominal values with a star superscript. So if you see that next to a variable, that's what it's saying. It's like our nominal value. And I forgot to mention, this is important for flight dynamics because you'll hear this more often. These nominal values, those are more commonly referred to as trim conditions. So if you hear like, what are the trim variables for this reference flight condition, they're talking about what are those nominal values I set these parameters to achieve this flight path. All right, now when you find these trim variables, some of them will be constants. So that's the most basic case. Like, for example, if we have wing level flight, that means that the roll angle is 0. So for that reference flight condition, it's some of these variables just have a constant. Or if you have a constant altitude flight condition, that means that the height variable is equal to a constant. Some of these variables are free. I'll put like some quotes around that. But all that means is that their initial values are kind of arbitrary. You can set them arbitrarily, and the reference flight condition will still be satisfied. So last time I discussed, one of the assumptions we'll tend to use in this class is a homogeneous atmosphere, meaning that the properties of the atmosphere are equivalent no matter where you are in three-dimensional space. Now, this isn't realistic because the density of air changes with altitude. But if I say I'm assuming a homogeneous atmosphere, then I'm ignoring that property. So what that does, if I say I have a homogeneous atmosphere, then if my reference flight condition doesn't specify a specific altitude, well, then that parameter is free, because I could set it to whatever, and using my assumptions, I can still satisfy your reference flight condition. Okay, some of these trim values or nominal values change with time. And this is a little strange. It can seem that way because usually when we talk about equilibrium points, we're talking about something that's just fixed with all time to a specific value. But when we're talking about linearizing a model about a nominal flight trajectory, you can think of like one of the trajectories we're going to look at today is a banked turn. So this trajectory is the aircraft is moving on a circular radius, and so like the direction is changing, but this is still a reference flight condition. But even though they're changing with time, it doesn't mean they're like free. These are going to be subject to some constraints that keep it on that flight path. Okay, and then one more point I want to make. sometimes for these trim conditions, there are many possible solutions. In other words, there's not just one setting for everything on the aircraft that makes it stay in this flight pattern. I think we brought up a couple examples last time, like you could be in certain situations where you're generating more thrust to compensate for a loss in like aerodynamic force, or if you can increase your aerodynamic force by changing one of your elevators or whatever, maybe you can turn down the thrust a little bit. So and we'll see some of that as we go, that some of this is up to you. And usually we'll choose these to minimize fuel costs and stuff like that. So just because you can do a certain flight pattern many different ways, when you throw on a layer of optimization where you say, okay, well, I want to do this flight path and minimize the fuel I consume, then that might make it into a unique solution. And if you guys are interested in like graduate school stuff, I highly suggest taking an optimal control course, because that's the type of problems you deal with there, where if there's more than one way to do a task, you ask yourself, well, what's the best way to do the task given a certain set of goals? So if you stay at UB, like Dr. Singh teaches optimal control, that was one of my favorite classes ever. I went to UB for graduate school. So just, yeah, keep that in the back of your mind. There's so many cool things out there. Okay, so let's dissect this, because last time we had the following reference flight conditions. So you kind of piece these together like Legos. You could have steady, wings level, non-turning, coordinated, descending flight. And if you don't remember the definitions for each of these, go back to one note set prior. But each of these has a specific meaning. So like steady means that U, V, and W are constant. And that also implies that V, alpha, and beta are constant. Let's see. This came from the wings level. These came from the non-turning. I believe this came from the coordinated flight. And we didn't derive this specifically, but the aerodynamic moments for this flight pattern they turn out to be 0 as well. But so I'm just showing you that when we looked at this reference flight condition, these are the constants that came out of it. We also had some free variables. This came from the homogeneous atmosphere assumption and also the isotropic atmosphere assumption. Isotropic meaning that the properties of the atmosphere don't change with direction. And I think most simply that just means I'm assuming that there's no wind. So it doesn't matter where I'm pointing the aircraft. I'm not going to be pointing into the wind or away from the wind, whatever. So that's why this heading angle turned out to be a free variable. We came up with some constraint equations. And where did these come from? We looked at how the conditions up above affect the kinematics and the dynamics. So you take our kinematics and dynamics equations, you substitute in the reference flight variables into those, and you find that the equations become much simpler in different cases. So we ended up with these constraints. And this is an example of where, like if I look at this, there's different combinations of thrust, aerodynamic force, pitch angle that will satisfy this equation. So there might be multiple solutions to this. So today, I want to do a couple more examples of analyzing reference flight conditions and like what variables come out of it, what constraint equations. So we're just getting more familiarity with this. So I think we're going to do 4 examples today, some of them longer than others. Okay, so what if we take this previous reference flight condition, the one that we just looked at, and that was a descending flight where we fixed the descent rate. We're coming in for a landing or something. What if we changed it so that we maintain a constant altitude instead? That is, you know, h dot's going to be 0. So now we're going to do this same reference flight condition. What is it? Oh, I went too far. Oh, yes. Steady, wings level, non-turning, coordinated. But so the way to visualize this is I'm just like flying straight through the sky at a constant altitude. There's no side slip. There's no turning. Just heading straight at constant altitude. So the constraint equation for the height, let's take this. I'm going to copy this. So I'm taking that same constraint equation. But now I know h dot's going to be 0. All right. So then this is going to be pretty basic here. I'm going to have these two terms equal. And then if I divide by cosine, I'm going to get this tangent term. And then if I bring u over to the other side, I get this. So I get this constraint on the pitch angle. So if I know my velocities, then I know the pitch. Okay. Now, we can also use wind frame variables. And what I mean when I say that is there's a conversion between u, v, and w, which are body frame velocities, to the wind frame variables, which are the magnitude of the velocity, the angle of attack, and the side slip angle. So if you're wondering about like what's the relationship here, go back to our wind frame notes. Okay. Okay, so let's go back to this equation. H dot's 0. But you'll find if I put this in terms of wind frame variables, this becomes the magnitude of that velocity times sine theta minus the angle of attack. And so how can this be equal to 0? We know this isn't 0 because I'm flying through the sky. My velocity is non-zero. So that means that this sine expression has to be 0. And this is going to require that the pitch angle is equal to the angle of attack. What does that actually look like? I put a figure in here so you can visualize it. Okay, so in order to maintain constant altitude, we have this condition. Okay, the pitch angle is the angle between the body, the fixed frame, like horizontal coordinate. So fx. So that's the pitch angle. And the angle of attack is the angle between the longitudinal axis of the body frame, so bx, and the relative velocity vector. Well, think about this, and this is kind of obvious actually when you see the picture. if I'm maintaining constant altitude, then my inertial velocity, well, it can't be pointing down like I showed here in the figure. It has to be pointing along this level direction, right? And if that's the case, what are you going to see? You're going to see that the pitch angle is equal to the angle of attack. So that makes perfect sense. That's a condition for level flight. It's kind of fun to me too. Like some of these conditions you can just think through and visualize, but I like it when, of course, the math is consistent with the intuition. So like I derived this condition purely from the mathematical constraints, and then when I say, does that make physical sense? Yeah, it does. You can look at the picture. Okay, so this is going to affect our other constraint equations as well. So one of the constraint equations for this problem related the thrust, the weight, and the drag, and so on. But look what happens here. I just figured out that the pitch angle has to be equal to the angle of attack if I want to maintain constant altitude. So then I'm going to have sine of 0 here, and this whole term goes to 0. So this changes to my trim thrust condition has to satisfy this relationship. The thrust times the cosine of my angle of attack has to be equal to the drag. Something similar happens with another constraint equation. Once again, this difference goes to 0. So then cosine of 0 is 1. So I get another condition for the thrust. The thrust force times the sine of the angle of attack has to be equal to the weight minus the lift. And this brings us to our second example, because we're gonna take this result right here and do some numerical calculations on the thrust. Okay, so let's take this reference flight condition from example 12.1, which we just did. What was that flight condition? We're flying straight in the sky, constant altitude, constant velocity. We're not turning, we're not descending or anything. I want to calculate what is my throttle input. And so we're going to make some assumptions here. So check this out. We're going to say the thrust is equal to the maximum thrust that I can produce multiplied with my throttle condition. And I made a note here. If you look at this equation, this is implying that this delta T, this throttle setting, has to be somewhere between 0 and 1. Because think about it. The maximum thrust I can produce is T max. So T star can only be equal to T max at the largest amplitude. So that means that the cap on this, it can only go up to 1. And then assuming that I can't produce negative thrust, the bottom end of that setting is 0. So think of this number as a number between 0 and 1, and it's just the throttle setting that the pilot engages. Let's assume that the maximum thrust we can generate is 40,000 pounds. The weight of the aircraft, 80,000 pounds. And let's assume that the way the aircraft stands right now, that the lift to drag force ratio is 4. So I'm just making a simple assumption that I have 4 times the lift than I have the drag. Let's also assume that the angle of attack is 0. Okay. Now using the constraints that we got just above, So we just barely derived these. Let's substitute in our assumption about this angle of attack. From the first one, we're going to get the thrust is equal to the drag. And from the second one, well, this is going to go to 0 because I'm taking the sine of 0. I'm going to have the weight is equal to the lift. Okay, now I know that the drag from the ratio that I assumed, it's going to be 1/4 of whatever the lift is. And because the lift is equal to the weight, which is 80,000 pounds, that means the drag is going to be 1/4 of that. It's going to be 20,000 pounds. All right, and then from equation 1 here, I know like thrust is equal to drag, so that's also going to be 20,000 pounds. And now that we know the thrust force, I can figure out what the throttle setting is, because it's going to be the ratio of the thrust force to the maximum possible thrust. So that's going to be 20,000 pounds over 40,000 pounds. And so my throttle setting is just 0.5. So that's we've constructed like one of the most basic possible examples of how we boil down a reference flight condition to one of the control inputs. Oh, I should put delta T here to be specific. All right, let's now look at a fancy turn. All right, a new flight condition. All right, we're going to say steady, coordinated, level. Now, level is different than wings level. It doesn't mean that our roll angle is 0. Level is going to mean constant altitude. Okay, so steady, coordinated, and we'll go through these one by one below. So, and we're going to be turning, and the specification for this turn is that this psi dot, that Euler rate, is a constant, and we'll assume that the other Euler rates are 0. And we're also going to assume that this aerodynamic force in the lateral direction on the aircraft is 0. Now, okay, let's talk about this turn for a second. This is a very important turn for commercial aircraft, particularly for this right here. So that side force being 0 is very important for the comfort of the passenger. I think I mentioned this in class before. When you turn in a car, you feel a side force. And if you take a turn really hard, you know, it throws you around, spills your drink and stuff. Have you ever noticed you don't feel that in an aircraft? And that's because they deliberately turn the aircraft in such a way that there's no side force. An aircraft has the luxury that it can roll and bank in such a way that this happens. When you turn in an aircraft, you feel yourself settle more into the seat instead of going to the side. So this is how you do it. Let's derive how it's done. Okay, so the steady condition, that just means that u dot, v dot, w dot, those are 0. P dot, Q dot, R dot, those are also 0. Or if we use these wind frame variables, those derivatives are also 0. So what does this imply? U, V, W, P, Q, R, V, beta, alpha, those are all constants. If we're saying their derivatives are 0, we're saying that these parameters are constants. What does coordinated mean? Coordinated means that the side slip angle is 0. That means you're going to have no relative wind coming at you from the side. Level, that just means that h dot is 0. We're not changing altitude. We have a specified turning rate where this Euler rate is a constant. If that's constant, it means that the yaw angle is just, it's a linear function of time. It's a constant times t, right? Let's see. Oh yeah, and then we also specified that these Euler rates are 0. So that just means that our bank or roll angle is going to be a constant. Our pitch angle is also going to be a constant. All right, and now here's where we got to do some hard work. The first thing you do is you identify, like, okay, what can I easily set to a constant value? Then you move on to your kinematics first and see how the constraints of the reference flight condition affect those variables. So let's look at the translational kinematics first. And when I say translational kinematics, I mean precisely this matrix equation right here. It relates x dot, y dot, z dot to u, v, and w. So, yeah, right. So this gives us 3 constraint equations on x dot, y dot, and z dot. But let's just focus on the z direction for now. So we won't like totally exhaust all of the conditions for this. I want to focus on this height. So if you multiply out z dot, if you multiply out this bottom row with u, v, and w, you're going to get this equation. So z dot is minus h dot, and it's the products of u and these like Euler angles, u, v, w. We can also incorporate the wind frame variables, and this is going to be important because we need to use the coordinated flight assumption where beta is equal to 0. So we have to translate this into terms involving beta. So this is from our study of the wind frame. U is going to be v times cosine of the angle of attack, cosine of beta. And so for coordinated flight, we just have to substitute in 0 for all these betas. So that means u is going to be v cosine alpha. V is going to be 0. And w is going to be v sine alpha. Okay, if we now substitute these in for u star, v star, and w star, we're going to find this. H dot is our velocity times cosine alpha, cosine theta, minus sine alpha, cosine phi, cosine theta. So I'm just substituting those things in. And then we know that the altitude is constant. So h dot is going to be 0. So this is going to give us, and you know, if this is going to be 0, we could divide by v and get rid of that. We're going to get cosine alpha, cosine theta is sine alpha, cosine phi, cosine theta. Oh wait, this should be, what did I do here? This should have been a sine theta. Sorry about that. So these guys, these are sines right here. And I can divide both sides by cosine, and then this will become tangent of theta. And then if I, you know, also divide by cosine alpha on both sides, I'll have tangent of the angle of attack. Times the cosine of that bank angle. So this is one of our important constraints. It relates the pitch angle to whatever our bank angle is and the angle of attack. All right, so that's the constraint we get from the translational kinematics as far as it pertains to the height parameter. So let's go on to rotational kinematics. So this is our rotational kinematic equation. And for this reference flight condition, it was defined for us that theta dot and phi dot are 0. So that's just given by the problem statement. So if I multiply this out, assuming 0, 0, P is going to be equal to, well, just the product of these two terms. And let's put all these superscripts on here to indicate that it's the trim condition. When we multiply out Q, it's just going to be that term multiplied with that psi dot. So it's going to be and finally we'll multiply out R, which is just the product of those two things. And we'll need these later. So we got something from the translational kinematics, we got something from the rotational, and now we move on to the dynamics. We've exhausted the kinematics equations, now we go to the translational dynamics. So this is our equation for translational dynamics of an aircraft. So let's break this down. We know, first off, this vector is 0. Why? Because the flight condition said steady. And steady implies u dot, v dot, w dot are 0. This vector is not 0. It can only be 0 if my aircraft is not turning, but we are turning. So we have to examine these terms a little bit. If you were to scroll up, one of the conditions we found is that V star is going to be 0. So like wherever I see a V, this is going to go to 0. So that simplifies things a little bit. And then here are these P, Q, R terms. We just figured out those constraints from the rotational kinematics. So I'm going to substitute in the product of everything here. So this term's going to be this times this. Basically, we have a lot of trig terms multiplied together. Let's get this one. It's going to be this. So we're just substituting in values that we determined earlier, and that's all that's going on here. Okay, so these values right here, these are what we're going to substitute in for that 3x1 vector right there. So we still need to look at this term. Don't worry, we won't write out totally everything, but this is that other term. We have this big rotation matrix, but thankfully these two terms are 0. So like the only terms that get multiplied out are the ones that interact with this non-zero term. So that's pretty nice. So if I multiply this all out, let's do that. The first row is going to be minus the weight sine theta plus t plus x. Let's put these superscripts on here. This one's going to be weight sine phi cosine theta plus y. And the last one, the weight cosine phi cosine theta plus z. So that's just the third row. Now you notice we have this 1 over m out in front. I can absorb this into here because the weight is mg, obviously. So this is like a more popular way of writing it. Minus g sine theta plus 1 over mt plus x. And then g sine phi cosine theta plus 1 over my. G cosine theta cosine theta. All right, so we're simplifying that out a little bit. Okay, so we have to add this term and that term because we had the whole translational dynamics equation, and so we figured out what all of those terms are. We got to add them together, and thank goodness, right? I wrote this out in advance. This is what you get when you add them together and set everything equal to 0. And we're just going to focus on this one right here. We won't focus on all three of these today. Something that you need to remember, this flight condition is a turn where we don't want anybody to spill their drink. We don't want anybody to feel any side force. So remember, we're assuming that the side force must go to 0. So we're going to have to figure out what all these other terms need to do to make that a reality. So we're focusing on the second constraint equation. We're substituting y star equals 0. That's a requirement from the reference flight condition. Also, a little bit earlier, we came up with this constraint equation. I want to be able to incorporate this condition into this equation to like simplify it even more. So I need a tan theta term to show up. So you can do that if you divide this equation by cosine theta. So it'll show up here. It'll show up here. Like you'll see, dividing this by cosine theta simplifies everything a lot, because like this is going to go to 1, this is going to go to 1, and then this is going to become tangent theta. And where that happens, I can make this substitution of that constraint. Okay, so doing that, let's say I divide by cosine theta. It's going to give us this. That term turned into tangent theta. The cosines disappeared elsewhere, and the side force, it's not here anymore. So this is what happens when you divide by that term. And then let's substitute in this constraint up here for tangent theta. That tangent theta term becomes tangent of the angle of attack times cosine of that bank angle. So just substituting that in. That's all we did there. We're going to simplify this a little bit more. Divide this now by cosine phi, because you see a lot of cosine phi terms in here. So you get, that's going to disappear. This is going to disappear. And then this term outside becomes a tan phi. So you see the cosine hasn't shown up here. It disappeared here. And then this became a tangent. We're going to simplify even more, if you can believe it. If you have the stamina left. So tangent of alpha times sine alpha. Tan is sine over cosine. So I'm going to have sine squared over cosine alpha. Oh wait, I don't want to write it like that. I want to say sine alpha. Yeah, that's the way I want to do it. And cosine alpha, that's the same as cosine alpha squared over cosine alpha. And then if I add these together, sine squared plus cosine squared, that's 1 over cosine alpha. So this whole inside simplifies to 1 over cosine alpha. All right, here's the final result. This allows us to solve for this bank angle over here. We get the tangent of this bank angle is whatever your velocity is times whatever your turning rate is divided by g cosine of your angle of attack. So that's just simplifying that equation up above. How does that second cosine alpha become raised? Good question. So all I'm saying here is that cosine alpha is the same as cosine alpha squared divided by cosine alpha. You agree? That's why. And the only reason I'm doing that is so that these terms share cosine alpha in the denominator. It's a substitution? Yeah. I'm just substituting this for cosine alpha. All right, now we're going to do one example where we show numerically what this looks like for a banked turn. We're going to use these constraints that we came up with. All right, so we're using this reference flight condition from the example we just did. And we want to find the roll angle for the aircraft and the pitch angle. In other words, these are the trim conditions for the roll and the pitch. Given this turning rate, given this velocity, 330 feet per second, which is 225 miles per hour. And let's say the angle of attack is 3 degrees. So we're going to use this formula that we just derived right up above. So the tangent of this bank angle is equal to this. So that's going to be 330 feet per second times 10 degrees per second. But when you take the tangent of an angle, it should be dimensionless. So instead of this being degrees here, I'm going to convert it to radians. So 180 degrees is pi radians. So that'll convert it to radians per second. Radians is dimensionless, by the way. If you don't know how a radian is calculated, a radian is a ratio of a length to a length. If you're curious about it, ask me about it after class. But just trust me, radians, they are dimensionless. It's a length divided by a length. Okay, so we're just filling in all that stuff. And you'll notice here, the only thing that's going to be left over is going to be radians. 1.7911 radians, but this is dimensionless in this case. Okay, so if I want this roll angle, I have to take the inverse tangent of 1.7911. And that's 1.0616 radians, or 60.83 degrees. I think this is the most important thing of how the side force is removed during a turn. You have to bank the aircraft. Okay, so we have that roll or bank angle. Let's get the pitch angle. So we had the following constraint equation. This was the other important constraint equation we found. The tangent of theta has to be the product of the tangent of the angle of attack, the cosine of the bank angle. So in the problem statement, we said the angle of attack is going to be 3 degrees. And we just found the bank angle to be 60.83 degrees. And if you multiply this out, you get 0.0255. So then to actually get this pitch angle, we have to take the inverse tangent of that. And that's going to come out to 0.255 radians or 1.46 degrees. It's interesting to point out here, you guys have heard of the small angle assumption. Like, you know, sine of theta is approximately equal to theta if theta is small. This same thing holds for tangent. And you're seeing it here. This is a small angle in radians, and the tangent of that is basically the same. Oh, wait. We could do... Where's this thing? We could actually visualize this. So we're making a turn. I believe these are the 3, 2, 1 angles. So the yaw, that doesn't really matter. The pitch is 1.46 degrees. That's probably barely noticeable. Yeah, it just tilts the nose up the tiniest bit. But our roll, 60.83. That's quite a bank. That's quite a bank right there. Well, we're going at 250 miles per hour. What was the yaw rate? 10 degrees per second. So that means it takes, okay, to go at 360 degrees, 36 seconds. So you complete a full revolution in about half a minute. A little over half a minute. And you're banked like this. That feels a little aggressive. That feels really aggressive. But you wouldn't feel any side force. You would be pressed into your seat, probably pretty intensely. We could calculate the acceleration in that direction. That would be I think it would be you take W dot and you subtract these two. We won't do that right now, but just looking at that image, I'm like, huh. This seems pretty aggressive right here. 60-degree roll angle. Guys, these are the examples I wanted to get through today. We're practicing getting those constraints, like what do they mean in terms of the equations, and it's a lot. So we're just trying to practice a couple different scenarios, some of these common ones, and get more used to it. But that's what I wanted to do today. We can come back to this. I don't know, Ian, are you still around? Were you enlightened since we talked about this earlier? I'm not sure. All right, let me see. Where'd this thing go? I don't know if this banked turn is the same as the example we just did. I mean, banked turn, it certainly means that the aircraft is rolling during a turn, or that it has a non-zero roll angle, right? Okay, so we measure the following accelerations and rates. This is the inertial velocity expressed in the body frame. That's the time derivative with respect to the body frame of the inertial velocity. The way I'm looking at this is yeah, I think this is just the instantaneous measurement of the velocity. This is not saying that it'll be this for all time. I mean, because it couldn't, right? If this is... If it's changing, then that means that a second from now, this is going to change. Or any moment of time from now, it'll change. But you can still... Also, the acceleration we were finding is also instantaneous. That's the only way I can make sense of this, Ian. That's the only way I can make sense of it right now. But if that's the case... Oh yeah, you still need... I was gonna say... Why do we need the velocity? You still need that because you're gonna have to take the cross product with that velocity vector. So it's important to know what the velocity is right now. So I think for this term, you substitute in those given values. Here you use the given instantaneous value. And then you can do it. That's my understanding of this problem. I'm curious if this is similar to... Hey, you're welcome, Ian. Glad to help. That's what I'm here for. Hopefully. I try my best. Okay. Yeah, so this can't be the same type of turn that we did in class, because this example assumes that those are 0. That is not assumed in the banked turn in the homework, so that must be a different reference flight condition. But yeah, think of it as instantaneous values. Have you guys done the, have you gotten to problem 3 on the homework? How's that one going? I think that'll be the cool one. Easier than last homework without using ODE 45. Yeah, it's true. You don't have to use... Yeah, you don't have to use ODE 45. Yeah, that's a little tricky with the interpolation within ODE 45. It's true. I do have office hours today, people. Is there any way you could post the solutions to homework 4? Yes. That will be posted very soon. I sent a write-up of that to the TA, and the TA's just finalizing it. So I think that'll go up within a day or two. Yeah, that'll go up, Vinny. That was a tough one. Because you're stuck on problem 3. Well, Vinny, on this... I hear you, yeah. This homework's a little different because you don't need to use ODE 45. You don't have to use any integration. Let me explain. Let's see. Where did this go? What am I looking for? Oh, wait. No, yeah, so like on homework 5, you're solving for the forces on the aircraft. So, let's see. In the MATLAB file that we give you u dot, v dot, w dot. We give you all of these values. So if you were to take the difference between those values in the mat file, and if you multiply them by the mass or whatever, that's going to give you all of these. That'll give you the sum of all the forces. Like here's the weight, here's the thrust, this is the aerodynamic force. So that's like what the first problem is asking for. It's asking for what's the sum of all the forces acting on the aircraft. but it's using these equations. All right, guys. I'm gonna close up the stream. I'm gonna be going to Discord for office hours for the next hour. So if you guys have questions, you can certainly come there. You're gonna move over to Discord? Okay, cool, Vinny. I'll see you there.